Welcome back, folks, to the third part of Lecture 7 of the Experimental Design and Analysis section of the Core Skills module. Before the break, we were looking at correlation, and we were looking specifically at parametric correlation using Pearson's test. Now we're going to move on to a situation in which we can't meet the assumptions of a parametric statistical test, and instead we have to use a non-parametric correlation, which is called Spearman's rank. Some of you may have encountered it at school. So, just to recap, we had these assumptions for parametric correlation. We assumed continuous normal data and a nice straight line relationship. If we violate those assumptions, for example, if the data are not normal, which we could test using a Shapiro-Wilk test, or if the relationship between x and y is obviously not straight, and the best measure of that really is actually to eyeball the data and have a look and see whether it looks like it's straight or curved. If it's obviously curved, then we violated the assumptions of Pearson's correlation, and instead we need to use a non-parametric test called Spearman's rank. These tests, both Pearson's and Spearman's rank, are dead easy to do in lots of different packages. You can do them in Excel, you can do them in R, in Prism, etc., etc. You get the computer to do the hard work for you. It will generate the test statistic and the p-value that you need. So let's have a quick look at an example of Spearman's rank using glycemic index in food. So this is a kind of a bit of a fashion, maybe it's kind of gone slightly out of fashion now, but people rating the glycemic index of food, which was supposed to be a sort of measure of how readily available sugars were in that food. And there was lots of interest in the fact that the sugar released from foods that release sugar quickly might give you issues with your blood sugar, because you'd expect if food's releasing sugar quickly that your blood sugar spikes, and that this might cause problems with people who are struggling on the sort of path to diabetes. So perhaps diets with high glycemic index, lots of readily available sugar, might be more prone to creating problems with diabetes. So we're going to look at some data actually about the glycemic index of food and people's blood sugar. And the question we're going to look at is whether foods with high GI tend to lead to bigger fluctuations in blood sugar. So we're looking at not just the sort of average level of blood sugar, but instead how much it varies. So this is the kind of thing that you get if you look at people's blood sugar over time. You get strong fluctuations in response to people eating food, because when you eat food, you break down sugars and that's released into the blood, which is all healthy and normal because you need that sugar in order to be able to do all kinds of important things. But the question here is, do you see stronger peaks and troughs, more variable blood sugar if you're eating foods with a high glycemic index? So we're going to look at the null hypothesis that there's no relationship between the glycemic index of the food and the amplitude, the average amplitude of these fluctuations. In other words, the size of the fluctuations. Do we see a really spiky up and down response, or do we see a more damped response, which is maybe what we'd expect with a lower GI? Here is some data. I actually had to make these up, so don't go panicking too much about the glycemic index of the food that you're eating. This is a fabricated data set, but the sort of principle, I got it from a real paper, the principle that there is a relationship. So what we've got here is the glycemic index of some foods, and then we've looked at people who've eaten these foods and measured the mean amplitude of the blood sugar levels. And what you see is apparently a positive relationship between the two, which is what we kind of expected, but it's not a straight line. It's very strongly curved. If you look at the right-hand side of the graph only, it doesn't look like there's much relationship at all, whereas on the left-hand side of the graph, it looks like there is quite a strong positive relationship. So in this situation, we've not met that assumption of a straight line relationship between x and y, so we shouldn't use Pearson's correlation. Instead, we should use the non-parametric equivalent, which is Spearman's rank. And Spearman's rank works just like Pearson's, but it does, as the name suggests, uses the ranked data rather than the raw data. So what you do is you take your blood sugar levels or amplitudes and you put them in rank order and turn them into ranks, the first data point, the second, the third, the fourth, instead of the underlying raw data. And then you can chuck it through this analysis called Spearman's rank, and it makes no assumptions about the distribution of the data or the shape of the relationship between x and y, and hence it gives you an unbiased estimate of p, the probability that this relationship could have arisen by chance under the null hypothesis. So it involves generating a test statistic, just like all other stats tests. In this case, it's Spearman's rank correlation coefficient, rho, this Greek letter rho. And for this data set, my made-up data set, rho is very, very high. Okay, it's nearly perfect, and actually you can see that this is a very tight relationship. So this is a very strong positive relationship between the two variables, and it's extremely unlikely to have occurred by chance. If I gave you the full p-value, you'd see it was like 0.0000001. Okay, so in this case, we've shown that there is a significant relationship between glycemic index and the amplitude of your blood sugar fluctuations. As I say, take that with a pinch of salt because I did make the data up, but there is published evidence that this relationship does exist, which is not surprising given that's what the glycemic index is really telling you, is how readily available the sugar is in the food. So we reject the null hypothesis and move on. That's all there is to say really about correlation. So I'm going to leave it there, and next lecture we're going to deal with, we go back to difference tests actually, because there's kind of rather more to say about difference tests, and we're going to look at some more complicated scenarios than we've looked at previously. Most of the time so far we've focused on comparing just two groups, and we're now going to look at comparing more than two groups, which produces some complications, but the principles actually of what we were doing turn out to be very useful, and we can carry on doing the same kind of thing using a form of analysis called analysis of variance, which is like an extension of a t-test. So we'll look at that next time.